Okay.
Go write my name on it. Hopefully it breaks.
So work, what is work? We need to talk about that.
Yeah.
Work is a physical quantity. Work is done when a force of some kind of type, there's all kinds of forces in nature. Who can tell me the 4 technical forces that exist in the universe according to known physics? Gravity, electromagnetic forces, strong nuclear force, and weak nuclear force. The only 2 you should probably be learning about in high school, gravity and electromagnetism, which are really electricity or magnetism, but they're really the same thing. So we learn about that in physics. But anyway, work is done when any kind of a force acts over a distance. Very nice. So moves an object through a distance. So it could be gravity, could be an electromagnetic force, anything like that, etc. And those aren't the only types of forces you have. Sometimes we talk about like frictional forces and other types of forces, but usually if you say like the force of friction, it's actually one of those other forces. It's just kind of in disguise. Okay, so there are other forces that you might hear about or that we might have in some of our problems. Okay, so in physics, when we do AP physics, we talk about work, but you know what? We only talk about work done by very specific types of forces because we are limited by no calculus. So we talk about work done by what kinds of forces, do you think? If we're limited. Constant forces. Conservative is also a good guess. But a constant force. And in that case, you know, there's this super simple formula for what work is. Work is just the product of how much force you're applying, how much you're pushing, or how much you're pulling if you have like a magnetic field or something. And it's just that times distance. How far you're doing that. How far you're dragging the sled, you know what I mean? That's how much work you're doing in a situation. So that's only for constant forces. Do you think that in everyday life there might be some forces which are not constant? For instance, if I grab Austin's hand and I try to pull him over this desk, I'm going to yank, and that's not going to be like a very constant force at all. Or even if I do it slowly, at first I might have to pull really hard to get him going, right? And then once he starts having some momentum, it starts to change, and I don't have to pull as hard. You know what I'm saying? So even simple things like that, is the force truly constant? No, it's definitely not constant. So that's where calculus comes in. Okay? So work done by a variable force, almost all real situations technically have a variable force. That is not just a plain product. What do you think it might be?
Probably got an integral.
It's probably got an integral from some A to some B, and it's an integral of what? Force times distance. Think about why that's an integral. Why does it make sense that this is an integral? If it's a variable force, wouldn't you like maybe just break up the distance into lots of little pieces? Lots of little pieces? And then just add them all up, and isn't that what an integral does? It adds them all up. In fact, it does it for an infinite number of small pieces, so that it doesn't matter how many times it's changing, how many times the variable changes during that interval. So this is the work done on what specific interval? On the interval A to B. It's like, you know, the distance between me and Austin or something, as I pull it. Does that make sense? So this is a nice application of integrals. So let's talk about a couple situations. So first of all, I wanted you to turn to page 489 in your textbook and just look at, in case you haven't had physics yet, let's look at some types of forces that we might be working with. If you had physics, you've seen them all already. If not, you probably recognize them a little bit, I bet. And then we'll get to some applications. So, what's one of the forces that we might have, the formulas? Force of what?
F equals KD, is that what you're talking about?
Yes. F equals KD.
That's spring
Doesn't
stuff.
usually have a negative in it because it's a restorative force. That's the force on a spring. That's called Hooke's law. So you might have some spring problems. We'll do one. It's easy. What other types of forces do we say?
Universal gravitation.
Gravity. So this is Newton's universal law of gravity.
Big G, M1 and M2 over R squared.
Yes.
Or maybe they don't follow.
So this is the gravitational force between any two objects you can possibly have in the universe if you ignore the gravity of everything else. Does that make sense? It's the gravity between this mass and this mass. And in physics, we go through why that's the equation and stuff. Yeah. Okay, and then another one for electricity is Coulomb's law, which is the force of electricity between two particles is
K,
some constant, charge 1, charge 2, and the radius squared. It's almost the exact same thing.
Yeah, except different.
Okay, so those are some of the most fundamental force laws that exist in physics. So we're going to probably be working somewhat with those, not completely, but you might need one for a problem, okay? So let's start with the book's second example, and let's see what this one's got for us. And I'm sorry if I'm going a little bit quickly, but we don't have a lot of time. So let's say we have a force of 750 pounds, and we've got a spring that force is acting on. It's compressing the spring 3 inches from its normal length, which is 15 inches. Okay? So we could kind of draw this if we wanted to. It might be useful to you.
Inches?
Yeah. So
What are inches?
this is an English book, not a very good physics book. Anyway, inside physics joke, sorry.
I got it.
750 pounds.
What do you say?
So the question is, what is the work for the additional 3 inches? Like when you compress it, that additional 3 inches, how much work is being done? So the law that we're going to use here is Hooke's law. You can put the negative in there or not, honestly, it really doesn't even matter. It can be absorbed into the constant, right? Like negative can go with the k. K is just a constant. So first what we're going to do is say, ooh, I think I left out a piece of information. No.
Did you?
So the 750 pounds compresses the spring 3 inches. So we can get the spring constant from that. So we get a force here, that's a force. We're looking for K, and we got that moved the spring 3 inches. Okay, then we're going to look at an additional 3 inches. Does that make sense? So this will give us the spring constant, and that just tells us basically how powerful this spring is. Yeah? So if we divide 750 by 3, what do we get? 250. So that's kind of a measure of how strong the spring is in this situation. So now, if we want to do the work we said,
The pounds per inch.
what is work again? Force times distance. Do you think that this is a variable force if you've just got a spring? Technically, it would be slightly variable, but this one would be so close to constant that in physics we don't even worry about an integral. So this is just a plain old force times distance problem. So we say the force on our spring for that additional 3 inches is going to be, I guess I can write it down up here. The equation is now F equals 250 D. Right? Oh, I did integrate it. Let's think. Is this variable or not? Todd said he thought it was.
I think it is.
Kind of, because it gets, it's like,
Remember
there's less here than there is
Yeah, like when the spring is really close together,
It's a lot harder to push.
there's like more force acting, trying to push outwards, and when the spring gets stretched out farther, that after it's gone 3 inches, it starts to get less. So it is a variable force, isn't it? We've got to be careful. What were you going to say, Chance? I'm sorry.
I just remember like a diagram of like the spring, like a horizontal spring.
Didn't we talk about that a lot? And how they
Yeah.
said
Sine curve.
we couldn't do it. Yeah, it was a sine curve for sure. So you're right. Very nice. Okay, so how should we do this then? What interval do we want to go from when we generate this work? Well, let's just say we start at 0. It's kind of a perspective thing. So 3, we're already at 3,
This is 6.
and then going to 6. I think I set up the problem not quite right. I should have written down some more stuff. So yeah. From 3 inches, an additional 3 inches out to 6 inches. That's what they're asking for. Okay. What function should we have going in there?
250D.
250. What variable do we usually like for like horizontal distances? X. Or we could put D. DD. You see why I didn't put D? Because then it would have been DD, and then we'd be like, oh, okay. I don't know what that means. Anyway, so we can do that integral. 250 x squared over 2 from 3 to 6. And that comes out to
Nintendo references.
3,375. Okay, what are my units here?
Pounds per inch. Work would be
So this is like
foot pound.
inch pounds.
Pound. God. Where am I as not units?
Inch pounds. Yeah, so we'd have to like go and convert that to what? What's work usually come in? Joules, right? Work is a form of energy. Good, okay. Anyway, we'll just leave it right there. Okay, let's see another example before we run out of time.
Well, make me do it drop. Yeah, you always make like me for dropping her.
That's about 6 inches.
Okay, this time let's do something with gravity. So, let's say we've got a space module, and our space module is orbiting the Earth at a certain distance. So let's say it's 800 miles above the Earth. So this part is 800 miles out to our space module. It's kind of fancy
Can we do like
space module out there. This is America, Paul.
Land of the free, home of the brave.
Yes, the physicists will be very mad at the Calc book right now. Anyway, so we're going to have 800 miles above the Earth. And what the question is, how much work is done to get it up that high? That's a very practical question, isn't it? Like how much work are you going to have to do to launch it up into orbit like that? Pretty practical. So let's write that down. Work done to get here equals what? They need to tell us the radius of the Earth, don't they?
4,000 miles.
It's 4,000 miles.
Assuming they don't expect us to spend that.
No, I hope not. So what law would we put in here to solve this problem if we wanted to get the work done?
Universal gravitation.
We'd use the law of universal gravitation. The book kind of cheats on this, and it just says, you know, you really don't have to worry about the constant of gravity and stuff. I don't know how I feel about it, but we're going to do it the book's way just to simplify things and get it done quicker today.
It's a magnitude of like
So
10
they just say it's some kind of constant
You can't just forget about that.
divided by the distance squared, distance between the center of the Earth and the object. Does that make sense? This is almost Newton's law of gravity. What's kind of missing here? The masses. So they're kind of ignoring the masses. I don't want to get into it too much. Okay, it'll work out pretty good. Anyway, so I think they should probably tell us how much weight this has. That's pretty practical. If we were trying to answer the question of you know, how much work is it going to take? What's our first question to the boss going to be? Well, how much does it weigh? How much am I going to have to launch up there? So let's say it's 15 metric tons. When we say metric tons, that's a weight. Weight is weight a mass. No, weight's not a mass. It's sneaky. That's something we do in physics. Weight is actually a force. So that's something we can plug into this to calculate that constant.
What is that? You can just shoot 15, really?
So 15 metric tons at that radius. What radius should I be thinking about? 4,800? But remember, what's the question we're trying to answer here? What do we want to do with this space module?
Find the work.
Find the work done to
Get it up there.
launch it from here to there, right? So if we're just trying to figure out what this constant for gravity is, if we don't know it, then wouldn't we care about what radius? Just the radius at the beginning, right? Like when it's sitting on the surface of the Earth. So we divide it into 4,000 squared. Then we can solve for c and get that constant, which then we can put into our integral when we integrate. Okay? So I got
That makes sense.
2.4 times 10 to the 8th. If we actually did this problem with f equals g/mm over r squared, we'd get the same answer. This is just a weird way to do it.
It's
But
weird.
it's not too hard. It's just like that last problem, right? You figure out a measurement like the 15 tons and being on the surface of the Earth. You plug that into the generic formula. You get a more specific formula. What's our now specific formula? This is just like algebra 2. You get a specific formula that says f equals that number divided by r squared. And then that's the force that's going to be acting, but now what are we going to do with that force? It's not going to be constant because gravity is going to be changing. There's going to be more gravity right here, close to the Earth's surface. As you get farther away, it's going to be changing. It's a variable force. Does that make sense? So we're going to now integrate and say the work is the integral of that force, 2.4 times 10 to the 8th. Instead of saying r squared, okay, we can do r squared.
Yeah, it's a radius.
dr. And from where to where?
Either 0
What radius to what radius? Remember, this tells you right here.
4,000.
This says what?
4,800.
From 4,000, because we want to go from there to there. And that's how much work. Yep. Anyway, I think if you plugged in like all the, because they didn't give us the masses of the spacecraft, isn't it more likely that they'll probably give us like the weight of something? So this is a more practical type of problem actually. This part up here, this number that we got, that would be gravity, capital G, the constant for gravity, times the mass at the center of the Earth and the mass up there. That's what that would be. So this totally matches what you're doing in physics if you're curious. It's just, they're trying to make it a little friendlier for us calculus people. Okay? Anyway, what's this integral going to be? That's going to be easy. Pull out the number. What's the integral of 1 over r squared, Chance?
Wait, what?
1 over r squared, what am I going to get?
1 over, natural log of r squared. Oh, yeah. So you get, r to -1 over -1.
Thank you, sir. And then I go from 4,000 to 4,800, and we'll get how much work we did. So I'm just going to write the answer down so we can move on. So I got 10,000. What are the units on this? They're freaky. They're freaking me out.
10,000 miles on.
Yes, Paul, very nice. If we had our computers out, then I'd say we could use do some unit conversion there. So I'll just tell you.
What is a
Yeah, they have it. So
Crap.
in English, you write work as what units? Foot-pounds. So this is equal to a certain number of foot-pounds. In any real situation, you don't usually use foot-pounds. Haven't you guys heard of foot-pounds though being required to like interact with things in space? I bet you've kind of heard of that. The real unit for work we're trying to get down to is joules at the end, but I'll leave that. I don't really care how you guys give me units. Give me units in any form, I'm good. No.
So do you put mile tons or do you put mile metric tons?
Metric mile.
It's mile tons.
At least it's metric.
Okay, 2 more. We got 2 more. We can make it. This is what snow days do to us in this class. Okay, so let's do something from chemistry. This one's fast. From chemistry. Let's talk about how much work gas does in like a piston. Like if you have a piston pressing on a gas, and that gas is like expanding or contracting. Something like that. So let's say we have gas with an initial volume of 1 cubic foot. More English. And pressure. I like it though. I mean, it gives us something new at least, right? Pressure of 500 pounds per. What do you think if we're in English and we've got a pressure? Pounds per. Good idea, but
Square foot.
Square foot. Yeah, good, smart. Pounds per square foot. So we're going to say that that expands to a volume of 2 feet cubed. And we just want to figure out how much work was done. Okay, so the more general law, if you've taken chemistry or physics, that you might be seeing in this problem is what? But, in our question, do we have like temperatures?
No.
Do we have numbers of moles?
Ends either.
No, so I don't think we have either one of these, and R is something most of you haven't even heard of yet, some of you haven't heard of.
That's just a constant.
It's just a constant, but so there's a more simplified version of this general law for this situation. What kinds of quantities do we have in our situation? Pressure and volume. So I think is it, anybody, can you help me? Charles or Boyle's law? It's one of the two, I forget which one. I think it might be Charles too. Anyway, does it say in there, Paul?
No.
I don't think it does.
Of course it doesn't.
It doesn't know. Okay, so the way that pressure and volume relate to each other for gases is they're inversely related. So pressure is inversely related to volume of a gas. So I can take some measurements. And what measurements do we have?
Sometimes it's nice to pay attention to fourth hour because it reminds me of all the inverse relations.
Yeah.
And
It is. And then that's a constant we need to solve for. And then we've got 1 cubic foot. So K is 500. So then what we're going to do here is say that work is the integral, and I'm going to write this down and then we're going to pick it apart and see why. The integral from, well, let's go, of P dV. When you think about why the heck that's true, I thought work was the integral of force times distance, not pressure times volume, right? So physics might help us. We'll have to ask our physics experts in the room. So I'm arguing that in this situation, the work done is not force times distance, because it'd be pretty hard to think about a gas in terms of distance, right? Gases are what?
they're
not well defined, right? They're like all over the place. They can change. So that's why we're going to talk about volume. Why is work this in this case? Let's see. What should we, if we're going dV, what volume should I integrate from? Can you guys help me with that part? That part's not bad. We said we wanted to check where it goes from 1 foot to 2 feet. That makes sense, right? The only question is, why is work suddenly pressure times volume?
The only thing I can think of is like if you think of a spring, it has a certain amount of distance, but in a gas you're containing it in a certain area, in a certain volume. And
So it's equivalent that way? Should we be able to work it out with units?
Yes.
What is pressure? Pressure is the force applied, there's their force, over area. What is volume? Area times distance.
Oh, interesting.
So PV, this is all V right here, right? Becomes what? Ha! So that's the same, right? And it makes sense that for gas you'd have to do this. So this is going to be an easy integral, isn't it?
yes.
Not a hard one.
So P is the const.
P is 500.
P is,
Oh, okay.
so we're going to go 1 to 2, 500 divided by V dV. Then we're going to ask Chance, what's the integral of 500 over V? What would I do with it? What would I do with this?
You'd bring it out.
Okay. And what's the integral of 1 over V or 1 over X?
Natural log.
Yes. Yes. Thank you,
He always wants to use
Mr.
it.
Aber. Yes.
Could be done.
Okay.
Circle left
See the difference between your natural log and your other thing now?
Yeah, yeah.
Good. Okay. So 500, then we're going to go natural log of 2. What's natural log of 1? 0, so we're going to get 500 times the natural log of 2. That's a little bigger than 500, isn't it? Something. 300 and something. Anyway, foot-pounds.
346.
Yeah, 46. You okay, Sam? A lot of physics going on, yes? You good? Mostly? Okay, maybe we'll talk later. Okay, I want to do one more. There's one more that's like a really interesting application. Let's see if we can get that. I'll take my own video.